Alright, good morning. Hope everybody's doing well. And looking like I might have to start taking attendance because we're getting down to the 50% part. But anyway, everybody who is here, so thank you for being here. Let's talk about makefiles. So this is going to be a big part of your next programming assignment, which I'll probably post tomorrow, and it will say you need to include a good makefile. So what we're going to talk about today is what I mean when that assignment says you need to include a good makefile. So I'm going to tell you exactly what that means, what makefiles are, how they work, why we use them, and what differentiates a good makefile from a poor makefile. So let's just jump into this. And we've talked about this before on a few different days, so let me just kind of run through it from the beginning. The basic idea here is we want to build executable programs out of source files. So your source files are usually .c files for us, and sometimes .h files that might include function prototypes, things like that. And so a typical setup might be you have a set of files, and these all need to eventually turn into some kind of executable, which I'll just think of as main. And we know that we can do this by just saying gcc-o main f1.c, f2.c, f3.c, f4.c. And that'll work, no doubt, right? This will compile all of these C files, it will give us an executable, and we're good to go. But this is not efficient, okay? The problem here is if I change one file like f3.c, which might be a very small file, when I execute this command, I not only recompile f3.c, but also f2, f1, and f4. And f1, 2, and 4 might be, 500,000 lines of code. That would be a ridiculously big file. But might be really long. And f3 might be a 10-line function, and by changing one of those 10 lines, I'm now recompiling, hundreds of thousands of lines of code. Okay, so this is not going to be a practical issue in what we're doing, but I want you to think of large-scale project development. Okay, I want you to imagine that you're working on a project with, 500 developers, each of them responsible for 30 files. Right? That's a lot of source code. So this also gets more complicated if you have, say, an include file. So you might have a file that contains function prototypes, or define statements, or structure statements, or type defs. Statements that you end up including in one or more of these files. For example, if you remember what structures are from CSE224B, a structure is a new type of a variable that has different pieces to it. So I could make a structure called a vector, and it could have 3 fields called x, y, and z, and each of those could be a double. Right? And then I can define a variable to be of type struct vector. Right? And to define the structure, I would say struct vector curly bracket double x, double y, double z. Right? Well, maybe I want to use vectors in this file and also in this file. So I would need to write that structure statement to say what a vector is in both of these files. And then if I change my vector, if I decide I want a 4-dimensional vector, I would have to change it in both places. So that structure statement I could put in a single .h file, and then I could number sign include this in these 2 files. Okay, we're going to go through examples of all of these things in a few minutes with actual code. But right now the point is, if my .h file changes, I need to know that it's included in these 2 pieces, and so I need to recompile f2.c and f3.c. Well, if I do this, right, I change my .h file, I just go ahead and I say compile everything, and f1 and f4 are getting compiled needlessly. Alright, so our goal is efficiency. We want to be able to efficiently build an executable out of source files in response to changes to one or more of those source files. And we want to do this by compiling as little as necessary, but making sure that we do compile everything that is necessary. So a way to avoid having to recompile all of these is to take each of these .c's and compile them down to what we call object modules. They're object files. So these are source files. These are object files. And object files are basically pre-compiled. Okay, they're C files, human readable, written by us, changed into a form that's really easy for the compiler to digest. It's gotten rid of the spacing, it's replaced variable names with something internal. It's figured out what functions are being called and what the basic logic is for all of your loops and assignment statements and everything. It's done the bulk of the work, right? And it's really left us with just a case where we need to sort of link together these pieces, these objects, into an executable. And a lot of the linking is, you know, this wants to call a function inside here. Well, the compiled function is already sitting in here, right? That's been changed into machine code. And the thing that's going to call it is already sitting in here, but it doesn't know where to find that function yet. Because the function isn't written in here, it's written in here. So what will happen when we put these objects together is what we call resolution of some of these addresses. The call to the function in F3 will get replaced with a call to an actual specific address, where that function will be loaded from this object. And linking is the weirdest part of the whole process to me, right? It's really kind of the magic of it all. Compiling is fairly mechanical, but linking really kind of needs you to understand a bigger view of the world, I think. But it's very efficient. So if we compile these things down to .c files, right, we say gcc-c f1.c, that creates an f1.o. And if we say gcc-c f2.c, that creates an f2.o. So this will create our 4 objects. And then to link these together, instead of linking the .c files, we say this. Right, so that links the objects together and makes our executable main. All right, what have we bought here? We've bought efficiency, because now if f3.c changes, all I have to do is this and that. I'm going to recompile f3.c to an object f3.o, and then I'm going to link my objects together. And I'm not recompiling f1, f2, or f4. And if f.h changes, and that was included in f2 and f3, all I need to do is recompile f2 and f3, and then link my objects together. Thank you. All right, so we won't notice a difference with the projects we're working on, because compiling all of our .c files, it's going to happen basically instantly. But again, imagine, you know, a few thousand files being linked together and having to recompile each one of those .c files. If it takes, you know, 2 seconds to compile this, you're talking about, you know, 40 minutes of sitting around waiting. All right, so this is what we're after. We want to be very tactical in what we choose to compile in order to rebuild our executable. Now the trick is, if I'm the one who's writing my code, if I've created these functions, right, I know what the dependencies are. I know if I change this .h file, what do I have to recompile? if I have other files in here that aren't part of this, if I have other versions of my main program that I'm not interested in, I know not to compile, you know, testmain.c, because that was something I was using for debugging, right? But if you take this collection of source code and you hand it to somebody because they want to make a copy of this program to run on their system, they need to know how to compile all of this stuff into an executable. Or if you come back to this later on, you don't want to have to remember all of these dependencies and nuances around making this executable. Or while you're developing your project, you don't want to have to be thinking about this, right? So this goes back to this mantra of mine, which is spend your time and energy on the thing that you want to be spending it on, which if you're writing code is writing code. If you're testing code, it's testing. If you're debugging, it's debugging, right? It's not, oh, what was that GCC command that I did? Up arrow, up arrow, up arrow, you know, try to find it. It's not, oh, I want to force this thing to recompile, so I better get rid of this .object file. We don't want to deal with that stuff, okay? We want to write code, we want to test it, we want to debug it. So there is a command on Unix called make. And make is the way that we process makefiles. So if you just say make, it will basically look in your current directory for a file called makefile. And makefile is a description of how to build something, for us typically an executable program. And a makefile is a collection of pairs of lines. 2 lines, 2 lines, 2 lines, 2 lines, over and over and over again. And your 2 lines look like this. Your first line begins with what we call a target, followed by a colon, followed by a list of dependencies. Things upon which this target relies. Our second line begins with a tab, and you can't fake this with spaces. It's got to actually be a tab character. So ASCII 9, Control I. A tab followed by what we call a recipe, a set of instructions for building this target. And then the third line is another target, and a tab followed by recipe. And then there's another target and a tab followed by a recipe, and so on. So it's a collection of pairs of lines. And if I say make, the make command will look for a file like this in my current directory, and if it finds it, it will look at the first target and it will try to build that. And here's basically what it does, and then we'll go look at specific examples. What it basically does is it says, okay, the person wants to build whatever this target is. It's usually a file name like main. And it says, well, what does that depend on? And we'll look for all the things that need to be present and up to date in order to build this. And if all of those things are found, then it will execute whatever this recipe is. It will run that command or commands, and it exits. Okay, but this whole thing gets highly recursive because these dependencies might actually be further targets that we find in the file. And so if I say this is dependent on f1.o, it will look to see what f1.o depends on to decide if f1.o is ready to go. And if f1.o depends on something that has been changed, it will use the recipe to rebuild f1.o and then come back up here and say that's satisfied. All right, so let's get away from the abstract. Let's put together a specific makefile for a specific example, and let's see how all of this works. So I'm going to pick on an example from the other day, which was just this sample main program. So we started with this kind of monolithic main program that one file, one function called main, prints a prompt, gets an input from the user, keeps asking for a new input until the input scans successfully as an integer, and then prints out the square of that integer down here. And we said, you know, this was not ideal because it's all one function, and that can get hard to manage. So we went to a version where we broke it into separate functions. So a greeting, a getNum, and a print result function. And then our main program became very small. Print out a greeting, get a number, print a result. And then we had separate functions for each of those three behaviors. Okay, this is all sitting inside one file still, main2.c. And so if I want to compile this, that's really my only choice. Now I could do this. I could compile main2.c to an object, main2.o. And then I could compile main2.o. I could link it into an executable. But that doesn't really buy me anything, right? Anytime I change my code in main2.c, so let's say I want to change my greeting here and just print out one message, right? I've got to recompile my C code, whether I'm doing it like that or I'm doing it like this. And I recompiled not just the code that I changed inside this greeting function, but I recompiled my main program, and I recompiled my getNum program, and I recompiled my print result function. So all this code got recompiled needlessly. So what we're going to do is we're going to split this up into pieces. Okay, so I'm going to make separate functions. Print result.c, getNum.c, greeting.c, and I'll just call this main.c. And I'll get rid of main2. Alright, so I have 4 .c files here, and I'm going to chop these up. So my getNum is really just going to do the prompting and ingest part. And I still need standard I/O because I'm doing printfs and fgets and scans. The greeting is just going to print out, you know, welcome to my program. The main program is going to just do our main loop, our main pass, right? So I'm prototyping my functions, and I'm going to call greeting, getNum, and print result. And then print result is just going to be my final output. All right. Now I'm not prototyping my function inside getNum, right? Because nothing in this file calls getNum. If I had something that made a call to getNum, I would need a prototype to tell the compiler what this call is all about. But what I'm doing here is I'm writing the function itself, right? And when I declare the function here, I'm saying it takes no arguments, it returns an int. So adding a prototype statement won't do any harm, but it doesn't do any good either. Okay, and the same thing with the greeting, right? I'm not actually calling greeting. But in my main program, I am calling these functions, so I need prototypes. All right. So I've got my .c files. I can compile each of those to object files, and now I have a .o corresponding to each .c file. And I'm just going to be lazy and compile star.o, and that created an executable called main, which runs my program now. Okay, the advantage of this is if I change my greeting, right, so I'll just change that message. I recompile that one.c file, and then I relink all of my objects together, and my program runs. And I did not recompile printResult.c, main.c, or getNum.c. All right. So this is a more nuanced way to build my executable. So what we want to do is we want to make a makefile which captures this knowledge about how to build our executable. Let me make one more change while we're here, though. Let me change my main program. Let me get rid of these and put them in a main.h file. Okay, so here I'm putting my function prototypes in because, you know, presumably if I'm breaking these things into functions, it's because these functions get used multiple times. So there may be other .c files that also need to know about these prototypes. And rather than explicitly typing in those prototypes here, here's what I can do. I can say include quote main.h, and that will say look in my current directory for a file named main.h, and the effect will be to pull the contents of main.h into my file right here. But instead of typing those in myself, I'm just going to leave that inside main.h, and then if I have to make changes or additions to that set of prototypes, I change it in one place, main.h. And then everything that includes that will see that new main.h. All right, the quotation marks say the actual file I want is main.h. The angle brackets are special. Putting in the angle brackets is like putting in double quotes /user/include/standardIO.h. We include so many files from this directory that there's a shortcut. If you specify a file name inside angle brackets, it's understood that it's in the directory /user/include. But we could just type this every time, but that's cumbersome and error prone and so on. But down here where I'm saying main.h, that means look for the file main.h in my current directory. So if I come in my current directory and I say show me main.h, that's the file that I'm including. And if I said # include /home/nick/main.h, it would look for this file in /home/nick. So this is an actual path. Whereas with the angle brackets, it's putting a prefix on it. All right, so there's our main program, right? And this is terribly clean, right? It's an include file. It's the declaration of main. Let me be good and put an int in the front. And then it's you know, what do we want to do? Greet the person, get a number, save it in I, print the result. And so someone asked in chat, are there ways we can modify what the brackets do? Yes, absolutely. So there's environment variables that specify that angle brackets look in /user/include, but I'm pretty sure you can change those to at least include other directories and probably to change where those angle brackets look. So there's environment variables you can set up somewhere in the GCC manual page probably. All right, so here's our cleaned up code, and we said if we compile the .c's to objects and then link the objects together, then we're good to go. So let's make a makefile which will describe how we build our executable out of the source code. So our makefile is called makefile, uppercase M, and it just sits in our current directory. And we can put comments in there and all kinds of other stuff, but let's just do a totally straight rendering from this template. Just pairs of lines, target recipe, target recipe. All right. So the first target I'm going to want to build, I'm going to want to describe in here is just main. That was weird. Main. All right, so I'm going to put in main colon, and I want to list all the things that need to be up to date in order to build main. And my plan in building main, remember, is I'm just going to compile my object files. So I'm going to list those, and I'm going to cheat. I'm just going to do an ls star.o. I'm going to read the result of that command into my file. I'm going to come up here and I'm going to shift J to join these. So that's a bit of a cheat. So main depends on these 4 files. Main does not directly depend on my include file, my main.h. I don't really care if main.h gets modified. I don't care if main.h gets deleted. If my .o files are up to date, I can build main. Okay, this is a subtle but important point. If my .o files are all up to date, I can build main. That's all I need. I can delete my .c files. If my .o files are up to date, I can build main. So main does not directly depend on my .c files or my .h file. It only depends on these objects. And if those objects are up to date, what am I going to do? Well, I'm going to say tab, and I'm going to say gcc-o main, and I'm going to compile those 4 objects into my main program. That's all there is to it. But where do those .o files come from? Well, they come from the .c files. So for example, getNum.o, that's another target, and it depends on getNum.c. And if getNum.c exists and it's up to date, how do I build getNum.o? gcc-c getNum.c. Alright, so let's do this for all of our files. So greeting.o depends on greeting.c, and main.o depends on main.c, and printResult.o depends on printResult.c. And I'm doing that editing by saying n to search for the next occurrence of a pattern, and then period to repeat my last change. So I changed this to printResult, and then I did an n to find getNum and did a period and a period. That's just VI stuff. All right, so this is looking like a legitimate makefile now. But I need one more thing. My main.c file does a number sign include main.h, which means if main.h changes, I should recompile main.c, because main.h gets included in main.c. It's basically part of main.c. So I'm going to add a dependency up here and say main.o also depends on main.h. So if either of these change, I'm going to have to rebuild main.o. How do I build it? By compiling main.c. Now I do not list main.h on this compile line. That would be kind of silly. I'm also including standardIO.h, but I don't say gcc main.c standardIO.h, right? The .h file is included in the source. Remember, there's a preprocessor. And before any compiling happens, that line where it says number sign include main.h basically gets replaced with the contents of main.h. So main.h goes inside main.c. right here. So all the code that's in main.h will get compiled because it's part of main.c. It's included in main.c. So I'm not going to list main.h on my GCC line. I'm just going to compile main.c. Okay, that's also kind of subtle, but pretty important. All right. Well, this looks like a good makefile. So what's going to happen when I try to make main? the make utility, it's a program, is going to run, and it's going to say, I need up-to-date versions of these .o files. And if those .o files don't exist, it's going to say, how do I create getNum.o? Is there a recipe for it? So it's going to look for a target called getNum.o, and it's going to see this right here and say, oh, here's a description of how to build getNum.o. What does it depend on getNum.c? Okay. And then it's going to say, well, I have getNum.c, hopefully it does, and it'll execute this command. Once it does that, getNum.o is now available and up to date. This dependency has been satisfied. It'll go on to this dependency. And it'll do the same thing. Oh, how do I build greeting.o? I need greeting.c. Well, I've got that. Let's execute this recipe, this command, and that'll build greeting.o. And after it's done that for all 4 of these dependencies, it will say, hey, I'm trying to build main. All 4 of these things that I need exist and are up to date. I'm going to execute the recipe, that's this right here, to build main. Alright, so let me get rid of my .o files, and let me get rid of my main program. So all I have in my folder right now is my source files, .c's, my include file, .h, and my makefile. Alright, so how do we use the makefile? We don't actually run it or execute it. We use the command make. And make will open this makefile, read the instructions in there, and then do the things it needs to do, hopefully to make that first target, which in this case is main. So I'm just going to say make, hit enter, and it's going to do the following. It's going to compile getNum, greeting, main, and print result down to object modules, and then it's going to link those together and create a program main. And now if I do an ls, you can see the result. All those object files exist, and the executable program main exists and does its thing. Now if I say make again, it's going to say main is up to date. How did it know that? Because to get main, it needed up-to-date versions of these .o files, and it checks the timestamp. And it says, hey, these were updated. Well, okay, it's more complex. It needs to know that getNum.o is up to date. So it looks at the recipe for getNum.o. It depends on getNum.c. And it will check the timestamps here. And it will say, you know, this was created at 11:20, and this was created at 11:30. So getNum.o is more recent than getNum.c. getNum.o is up to date. And it'll do that for greeting and main and print result, and it will see that all of these are up to date. And it will look at the timestamps on those, and the last one of those was created at, say, 11:32. And it'll look at main and see that was created at 11:35. Well, main is more recent than the things it depends on, so main is up to date. Now if I get rid of that .o file for greeting, and I say make, it recreates greeting by compiling greeting.c, and then it links my objects together. And now if I say make, it tells me everything's up to date. If I change a file, so let's shout a lot. Right? I don't have to say GCC, just say make. And it'll figure out, oh, greeting.c changed more recently than greeting.o, so I'm going to recompile that. And greeting.o is more recent than main, so I'm going to rebuild main using greeting.o. And it does all of that for you. And now my program is up to date. And if I'm not sure, you know, if maybe I made some changes, I'm not sure, I can always just say make, and if everything's up to date, it'll tell me, and it won't spend any time compiling or linking. Alright, let's say I make a change to my include file. So, I don't know. prototype some non-existent function. I don't know if that'll give me problems or not. Let's just say I add something in my include file, right? And I want to remake my program. It knows that main.c includes that file, so it rebuilds main.c, and then it relinks all my objects. Now, if for some reason, let's say greeting.c also included that .h file, I could add a dependency here, main.h. I don't actually include main.h and greeting.c, but make doesn't know that. Make is just looking at my set of instructions here, my makefile. Right? If I decide to include a dependency on main.h and it's not actually dependent on it, that's on me, right? Doesn't really concern make. So I say make, well, now it realizes, greeting.c depends on main.h, and main.h got changed recently. So it rebuilds greeting.o and then links everything together. And if I say make again, everything's up to date. Now if I change my include file again, and I say make, the instructions know that I have two C files that depend on main.h, greeting and main. Those both get recompiled to objects. Those objects get linked together. I end up with an executable program. All right, so this is glorious once you have a makefile in place, because you never type GCC again. You never have to think about, I changed an include file. Where do I include that? So you start searching to see, right? Or you've got, 3 different versions of greeting, and 2 of them were test versions, and maybe greeting 5 is the real one, right? Well, that's not great naming convention, but if that's what you want to do, in your makefile, you just set up greeting 5, right? And you're not saying gcc star.c, which if you have more than one main program in your directory, compiling star.c will get you in trouble. The makefile contains all of that information, all of that knowledge about the structure of the project. And particularly as more and more people are working on this project, that's really important information, right? To know the dependencies and the instructions for building objects or executables. That knowledge might rest with several people, but you have one makefile that encapsulates all that knowledge, and now anytime that you make a change, anytime somebody else makes a change, anytime you move to a new architecture or whatever, you just say make. All right, so that's the basic motivation and the basic setup. Let me show you an example of a bad makefile. Okay, technically this will work. If I say make, it will build my executable program main. Okay, but this is not efficient. This is not the idea of a makefile. This I could just put in a shell script called, compile. And I could say compile, and it would just be one line that says do this. Because this makefile is always going to do this, right? Anytime my C programs change, it's going to go ahead, it's going to recompile all my C code, make me an executable. So on your next programming assignment, I'm going to specify that I want a good makefile, okay? This would not constitute a good makefile. This would be a poor makefile. A good makefile is something like this. Something that pays attention to the dependencies and does selective compilation. So I'm going to want to see that all of your C files get compiled to objects, one by one, based on the dependencies for each object, and then those get linked together into an executable. And the test is, if you change one .c file and you say make, does everything get recompiled, or do just the things that get modified get recompiled? So as part of this, I'm also going to require a certain number of separate files for your program, and I'll specify that in the assignment too. I'm probably going to require 3 or 4 separate files, including having the main program in its own file. But I'll spec that out when I write it up, and we'll talk about it probably tomorrow or Thursday. All right, so there's another aspect to this. Let me get rid of that bad makefile. So let's say that I've got a new version of the compiler, right? Or I've changed my compiler switches. You know, because I have my GCC set up like this. And let's say I have a different version of the compiler, and I want to rebuild my project, and I say make, and it says main is up to date, right? I'd like to force it to rebuild my project from scratch, to recompile all of my .c files. Well, again, I wrote this, so I know how to do that. I can remove my main program, and I know that I can safely remove all of my .o files. But you know, if this was somebody else's work that I was working with mine, I wouldn't want to just delete all of the .o files, right? Or the main program. I might not even know what the different pieces are. So I can do this because it's a small project, and I can say make, and it forces it to recompile everything. But if I hand this to somebody else, if somebody downloads this from the web, and they want to build it for their Raspberry Pi, which is a different architecture, which means everything needs to be recompiled, they don't necessarily know that this is the right thing to do. And if they have other object files in their directory that they want to keep, this is definitely not the right thing to do. You don't want to just remove all your .os. So here's something else that we do inside our makefiles. We add kind of a bogus target called clean. And this is pretty standard. So you can use makefiles for anything. They don't have to be used to compile C programs into executables. You can write makefiles for Java or Python. You can make makefiles if you do text processing, like with LaTeX. You can set up all the commands you need to you know, process your text file and make the bibliography and put the pieces together and turn it into a PDF, right? Anything that you're doing along the lines of building some finished product, where there's a series of steps and those steps depend on which steps have been done, there's a good chance you can get a makefile to do that. Okay, it's a general utility, but what we're using it for is primarily compiling code to make an executable program. But here's something else that we can put in our makefile. We can add a bogus target called clean. And I'm not going to list any dependencies for clean, but I'm going to say that in order to build this target clean, what do? I remove main, and I'm going to remove all of these .o files. Now, if I just say make, it always tries to build the first target. But if I say make greeting.o, it will look for a section that says, you know, for a target greeting.o, and it will look for those dependencies and then apply this recipe. So if I say make space clean, it's going to look for a target clean. It's going to find it right here. It's not going to see any dependencies, and it's going to execute this recipe, which is really just a Unix command for removing the things that the makefile built. So if I say make, it tells me main is up to date. If I say make clean, it removes all the stuff that was built by my makefile, and now when I say make, it actually recompiles my source code from the beginning. So most makefiles include a clean option. It's a really convenient, safe way to say, hey, I don't care which dependencies have been satisfied already. I want to rebuild everything from scratch. And so you say make clean, and then you say make, and you're good to go. All right, along the same lines, another thing you find in a lot of makefiles is a target called install. And the idea here is maybe you're making, you know, a game that should be made available to everybody. So after you compile it all and you link all the objects together, you have an executable. That executable is going to be in your current directory. Maybe you want it to be in some system level directory, and you want it to have certain permissions. So you could make a target called install, and here I am going to say this depends on having an up-to-date version of main. And the recipe I'm going to use to build install is just copy main to, let's put it in /temp, and then let's change the permission of that to 755 so that everybody has access to it. Right? And this is not a compiler command. This is not a linking command. This is not creating a file called install. It's a trick. I'm setting this up so that if I say make install, the make program will say, oh, okay, let's look for main, and if main exists and is up to date, let's copy it to this directory and let's make it available to the world. So now if I've just downloaded this system, I can say make clean to get rid of anything that might have already been built. I can say make to compile everything together, and then I can say make install, and it'll move it into the target area. And there it is. And it's readable and executable by the world. And if I modify my include file and I say make install, what's going to happen? A whole bunch of stuff. I said make install, and the recipe for that is, you know, copy this file to /temp. But it very smartly and correctly recompiled greeting.c, main.c, rebuilt my main program, and then copied that. How did all of that happen? Just by saying make install. Okay, this is the magic part here. This is the recursive part. We got 2 minutes here. When I say make install, it says, okay, to do this I need an up-to-date version of main. So it pauses right there and it says, is main up to date? Well, it goes through the makefile and it looks for a recipe for a target. It looks for a target named main and it finds it. And it says, oh, there's main. Okay, I need getNum to be up to date. And it will look at getNum, and getNum.o depends on getNum.c. And getNum.o is newer than getNum.c, so this is fine. It gets to greeting, and it says greeting.o depends on greeting.c and main.h. Main.h was newer than greeting.o. So this dependency is not satisfied. It needs to build a new greeting.o, so it executes this command. And now greeting.o is up to date, so this is satisfied. Same thing happens with main, and then with printResult.o, it was newer than printResult.c, so that was satisfied. All these dependencies are satisfied, so now make executes this GCC command, and now we have a new version of main. And now we go back to where we were, which was we were trying to make install. And it says, well, I need a new version of main. Do I have one? Yes, I do. Main is fully up to date, and so it executes this command, which copies main to /temp. But all of that is being done for you. That's why you want to make file, right? So that when you change something in your code, if you want to rebuild an executable, you just say make. If you want to push it out to your area, we're not going to do make installs for our stuff, probably. But you know, you could have your make install push it over to Git, for example. But we don't usually push executables. But whatever you want to do, right? Change your code. Spend your time thinking about writing code, testing code, debugging code, not about how to compile it. If you want to compile it, just say make. Okay? So make files in the beginning of your project when you've only got 1 or 2 files, and keep it up to date as you build. Don't wait till you finish your whole project and it's working perfectly and it's due in 2 hours, and then sit down and try to build a make file. Okay? That's asking for disaster. So make your make files from the beginning. All right. That's really all there is to say about makefiles. It'll be worth points on your next programming assignment, and we'll talk about that tomorrow and or Thursday. All right, have a great afternoon. I will see you tomorrow.